Welcome back, everyone, to the afternoon session. Today we have Hadi Kharaghani, who's going to be telling us about balancedly splittable orthogonal designs.
Okay, thank you for the organizers, particularly Chris, for letting me know. And I had to rush to prepare this talk. So some of the talks, Chris and perhaps Bill have already heard part of it. So they have to be patient because um, there's going to be something new, right? Okay. So a Hadamard matrix is a very simple matrix, entries plus minus one, rows are orthogonal, so the columns are orthogonal. Just a reminder, and I will denote every Hadamard matrix of order n by Hn. And of course, as a very simple exercise to show that if there is a Hadamard matrix, then the order must be either 2 or a multiple of 4. And then, of course, the big open problem is a conjecture which has been unresolved for about 117 years now. There is a Hadamard matrix of order 4n for each natural number n. And this conjecture is confirmed for n less than 167, which shows how much we know really about this conjecture. Almost nothing really. And of course, there's a small open problem. And that small open problem is there is a Hadamard matrix of order 4 times 167, which is 668. So that's the first order which is not known. Now, 167 minus 1 has only two divisors. The divisors are really, one is 2 and the other one is 83, which is a prime. So it really closes, the door to some algebraic, perhaps, search for this matrix. And it seems, at least, from what we have from experience, that the only way remaining is finding perhaps, a Turing type sequences, which are actually quadruples of -1 sequences, A, B, C, D. A, B, C, D are each of length n, and D is of length n minus 1. And the sum of the non-periodic, you have to take actually one of A, one of B, two C's and two D's, and find the non-periodic autocorrelation, and we should get 0. So for the non-periodic autocorrelation, just a reminder, so you have a sequence A1 to AN. You shift the sequence and then fill in the space with 0 and find the dot product of the two rows. You do this for all these matrices, 6 of them. Add them up, you should get 0. Now, doing this actually allows us to really put these sequences together. And you can see that if you take one of A, one of C, one of D, we get 107. And B, C, D. Indeed, the way it goes is like this. You take CD and make really a sort of imitating from the Goulet pairs. You take two CDs, put them together, and then negate D and put with the C together. And now you add A to 1 and another A minus to the 1, and then you put B and B minus. And then you get 4 sequences. These 4 sequences of length 107, or for the case of open is 150, 167, and then you can just easily find the corresponding Hadamard matrix. indeed, you know, if you have a Turing type sequence of length n, and n minus 1, you can always have an Hadamard matrix of order 12 n minus 4. And indeed, you know, it was the Turing type sequences of length 36, 36, 37, 36, and 35, which led to the Hadamard matrix of order 428. And if we try to do this with Turing type sequences, you have to really consider sequences lengths 56, 56, 56, and 55. And you can see that the gap is really huge. And it seems really this is the remaining way. Although I have seen lately, you know, there are some new attempts, and one really expects, you know, within 2 or maybe within 1 or 2 years, again from past experience, one expects really that the order 668 may be resolved. There is absolutely no doubt that these matrices exist. There's a lot of them actually. For each order, there are billions of them. As a matter of fact, order 36, there's so many of them that their counting is really almost impossible. 32 has been counted, but it's about 13,700,000 something, you know. So 36 is not at reach even right now. Anyways, however, one has to be careful, you know, that the Turing type sequences of length 38, 38, 30, 37 was found, you know, by one of my students. And the Turing type sequence of length 40, 40, and 39 was a PhD thesis at the University of Chicago. And of course, you know, the student also classified all of those of that certain length. So theoretically, it's just impossible really to follow up on whatever method which existed right now and really find this Hadamard matrix order 668. Now here is the Hadamard matrix of order 16, and it's been halved. There are two parts. There's a blue part and there is a red part. Now the red part has 6 rows, and of course, you know, the blue part has 10 rows. And the reason that we really are interested in halving this matrix like this is because of, if you pick, let's say, the red part and you call it F1, then you have an example of a frame in R6. This morning, Joey get a fantastic talk, you know, and fortunately, now I don't really need to go through reminding you. Of course, you know, a frame, it means, you know, that these 16, if you consider the columns as vectors, then they span actually R6. And and if you consider each of these vectors as a line, then we get actually equiangular lines, 16 equiangular lines in R6. And as Joey mentioned this morning, this is actually the maximum we get for R to the 6 from a certain given angle. For different angles, you get actually different number of vectors, but for this you get 16, and of course it's flat too. You know, every element has the same magnitude. Now, why is this really a frame? Is because the products of the columns actually gives you either 2 or -2. It means if you find F1 transpose F1, you're going to get on the diagonal 6, which of course shows the weight of the vectors, and off diagonal you either get 2 or you get -2, and that really tells you really why they are equiangular. So indeed, really, if you really drop, you know, the condition of linear independence from the vectors, then of course you look for a better way of really finding basis. And this is actually a sort of basis as was given in this morning's talk. Indeed, we actually have, this thing is tight. tight shows really the rows are actually orthogonal. So because the rows are orthogonal, so it's tight. Namely, you really the span is giving you all of the space. Now, a frame, we call it flat if the absolute values of all the entries stays the same as it is. Now, there is a second actually frames hidden in that matrix. And that is again, is consisting of 16 rows in R6. And indeed, that one is also another frame. And putting them together, you're going to give, it's going to give you a Hadamard matrix where you can see actually 4 frames. This is, look to the columns, this is 1, this is 2, look to the rows, this is 3, and this is 4. So you really get 4 frames from one Hadamard matrix. And that's the reason why really we like really to study this property of Hadamard matrices. Okay, so let me define now what we call balancely splittable Hadamard matrices. We say that Hadamard matrix is balancely splittable with the parameters n, L, A if by suitably permuting its rows or columns, it can be transformed to H2, H1. And of course, H1 is L by N, and K1 is N by L, and all off-diagonal entries of H1 transpose H1, or K1 times K1 transpose belongs to the set A minus A. This is what we call, balancely splittable. Of course, the definition is more general than this, but I don't want to get into the more general definition of balancely splittable Hadamard matrices. And yeah, this theorem really shows why really these things are interesting. If we have a balancely splittable Hadamard matrix with the parameters NLA, then the followings are equivalent. Number one, if you subtract H1 transpose H1 minus H2 transpose H2, so you pick up the lower part of the Hadamard matrix, which was, if you remember, was red, and multiply the columns and then and take the upper part, subtract, you're going to still get another Hadamard matrix if you divide it by 1 over 2A, just to make those plus minus 2 into a plus minus 1 in that particular example. And of course, the L has no choice. Number one, the order of the matrix must be square, and L is either n plus the square root 2 over n or n minus the square root 2 over n. The upper part is always n plus the square root n over 2. Lower part is n minus the square root n over 2. Now, in this case, of course, the n is a perfect square, and furthermore, the matrix that you get from from the first part, the K, is unbiased with respect to the original matrix. Unbiased, just the definition is right there here. So it means, if you multiply 1 to the transpose of the other one, you're going to get a multiple of another Hadamard matrix. And you can see that this Hadamard matrix is H1 minus H2. Just the original one's a little bit changed, right? And so really, you can see that it's really giving you some reasons really to believe that if you can really show which of the Hadamard matrices are balancely splittable and which perhaps are not. Okay. Now, some remarks here. A Hadamard matrix for the n is called regular if the row sums and column sums are all the same. And in this case, of course, the order has to be squared because the row sum column sums becomes the square root of n. And any balancely splittable Hadamard matrix with parameters 4n squared and 2n squared minus n is equivalent to a regular Hadamard matrix. Two of the Hadamard matrix, not every Hadamard matrix is actually balancely splittable. The smaller one, order 16, there are 5 of those, and 3 of those are equivalent to a regular Hadamard matrix. 2 of them are not. So obviously those 2 are not balancedly splittable. So the issue here actually also becomes, which one are balancedly splittable. And furthermore, a counting argument, which actually is not a simple counting argument, shows that if the order of the Hadamard matrix is an odd square multiple of 4, then it is not balancedly splittable. For example, order 36 is not balancedly splittable. As I said, that the argument here is not simple, but it is true. Okay, so now let me talk about orthogonal design. One way of extending, of course, Hadamard matrices is to allow the entries of the matrix to be variable, to be indeterminate, rather than being a fixed plus minus 1. Let it be really entries like A, B, C, D, and so on. What is really important, and it says the same, is the general property of orthogonality. The orthogonal, we're really studying the general properties of orthogonality. Now, a weighing matrix, again, is the one way of generalizing Hadamard matrices if you allow the element 0 also in the matrix. So if you allow element 0, and again, you assume that the entries are 0 plus minus 1, rows are orthogonal. Again, orthogonality has been kept. So you get a weighing matrix. And of course, if there is no zeros, the weighing matrix becomes a Hadamard matrix. So that's one way of generalizing. But more general is an orthogonal design. So an orthogonal design has a type S1 to Sn, and is a matrix of the form that you can break it into sum of smaller matrices, x1 w1 plus x2 w2 to xu wa, and the variables we call x1, x2, xu to be the variables of this orthogonal design. Each of these wi's are actually weighing matrices, and the weight of these weighing matrices are those s1, s2 to su. So let me give you some examples of Hadamard of orthogonal design. This is the simplest but the most useful OD order 2, and the variables are AB. As you can see that the rows are orthogonal. The variables are assumed to be commutative. So, and the next one is an OD 4, 1, 1, 1, 1. So there are 4 variables, each one repeated 1, and then again the rows are orthogonal. Now, if you have an order which is not divisible by 4, but still you can have a weighing matrix. And you can see here, we have a weighing matrix 6, 5. As a matter of fact, this has also a name. This is called the conference matrix. We actually can assume that if you multiply this by A, we can assume this is an orthogonal design of order 6. And in one variable, only one variable. Okay, so let me give you more examples of orthogonal design. Here is another one, and indeed, this is a very, very useful one. It's an OD of order 8, and there are 8 variables. Each variable is repeated once. Those bulk force face letters means negative of the number. And this next one is order 12. There are 3 variables, each one repeated 3 times in each row and each column. Okay, so there are many open questions related to orthogonal designs, many, many open questions. And most of them are really elusive. They're not really something that is easy to handle. Number of course, because of the condition of orthogonality, the number of variables in any, actually, I'm interested in full orthogonal designs in this, I said full orthogonal design. In any orthogonal design is restricted to the radon numbers. And the radon numbers is you take out all the twos that the order has, and then follow up the procedure. As you can see, the rho n is 8 times q, and plus 2 times r. R is between 0 and 4. And here are some few values of rho. So if k is 1 is 2 variables, and 2 is 4 variables, 3 is 8 variables. And then, you know, from orders 16, there are 9 variables. Order 32, 10 variables. Order 6 is 12 variables. And order 7, there are 16 variables, and goes, you know, according to the formula up there. And I put 7, 16 in red because we really don't know much about 16 variables really in Hadamard, in an orthogonal design of order 128, 2 to the 7, 128. We don't even know one single orthogonal design with 15 variables, let alone 16 variables. And indeed, this is my open question too. And the open question too must be a simple question. It is there an orthogonal design of order 128 in 16 variables, each one repeated 8 times? This has nice application if it is found. I have spent a while of time on this one, but unfortunately, no success. Okay, so here I have an example of balancedly splittable orthogonal design. Indeed, as you can see here, I have 2 columns of blue and green. Each one of these columns form a frame. Now, if you look at the blue one, each row has 3 of the variables. And furthermore, when you multiply the 2 rows together, you're going to get a fixed number similar to what we had in Hadamard matrices. Indeed, I'm now take, you know, the vertical. The reason I'm really taking the vertical is because the construction I'm going to give you later on always gives me, you know, the vertical ones are more interesting than the horizontal one, although the horizontal one are also balanced, but the vertical ones are more interesting. So if you take really the first, let's say the blue one, you call it F1, and the red one, let's call it F2. What really happens is something really interesting. When you multiply F1 by its transpose, you're going to get, as you can see here, you're going to get on the diagonal 3 times a squared plus b squared. Off diagonal, either you get minus a squared plus b squared, or you get plus a squared plus b squared. So obviously, really, this is really giving you, if you put for a and b equal to 1, you're going to get a balancedly splittable Hadamard matrix. But of course, in here, you have much more freedom. A and B can be taken any numbers, right? Not only that, also F2 also is a frame. You're going to get the same nice property for F2. So it's actually a gift that you get always from Hadamard matrices. It always comes in a twin when you really get well, I have to correct my statement. If the way that I really construct, you always get twins for orthogonal designs. Okay. Now, a definition of balancedly splittable orthogonal design is just simply you can split it into 2 parts in such a way that the x1 star x1 is in the set. You can see that there are 2 values off diagonal. Now I put in here a star because the construction I'm going to give you is going to be good for complex Hadamard matrices, is going to be good for quaternic Hadamard matrices. So that's why really we should take conjugate transpose actually rather than only transpose. So here again I'm showing you the one there. You can see that there are again, you know, you can see there are two vertical splittable and also two horizontal one. Always comes as you can see here. Okay, now here I'm going to give you a construction, and I hope you are patient enough really to see the construction. Of course, you know, is not trivial, and I have to say that I was really lucky. We were actually lucky that we could really find, you know, this construction. Indeed, you know, the construction has 9 parts, and these 9 parts has to be constructed small parts, and then add the second small part, and the next one, and the next one, and the next one. So at first, I have to tell you how you construct A and how you construct B. In order to really make it as simple as possible, I'm really going to do this for a very simple thing, the one that you have given. I have given you the example, and you have seen it before. Namely, you know, I'm going to do it for an OD211. So we take, you know, the orthogonal design, the simplest possible one, AB, B minus A. And of course, if you put now for A, B equal to 1, you're going to get a Hadamard matrix H2. Now, we now construct two what I call auxiliary matrices C1 and C2. And this is how we do, you know, we pick, you know, the first column from Hadamard matrix, the first row from orthogonal design, and again for C2, second column from Hadamard matrix, and second row from orthogonal design. And we make up actually 2 rank 1 matrices. And you can see that, you know, if you pick, you know, let's say the row 1 from here and the row 1 from here, they're orthogonal. Every row from the top one is orthogonal to every row at the bottom. So this orthogonality property here is going to help a lot. Indeed, you know, we now, I'm going to now introduce 2 block sequences, C1, C2, and C2, and C1, C2 minus C2. This forms a block Golay pair. Now, I don't want to go into really talking about Golay pair, but this is really how you really make up the matrix A. You take the circle on the block C1, C2, C2. So as soon as you have the first row, you have the second row. You just shift the first row 1 unit to the right and move C2, you know, to the first column. And do now the same with the third one. So this is this comes really from a Golay pair, and B is circle and C1, C2 minus C2. The reason that we put minus C2 is because we want to have the autocorrelation of the C1, C2, C2 and C minus C2 to get 0. You can see that, you know, that these two are actually orthogonal to each other. These two are orthogonal to each other. So you're going to get, you know, when you really look to the multiplication of the 2 rows, you're going to get a C2 squared here. And of course, in here that you get a minus C2 squared, and they get canceled. That's why really they form a Golay pair. It means, you know, when you really look as blocks, you're going to get a Golay pair. Now, the reason that I was really familiar with the Golay pair helped me really to come up with the construction for A and B. However, of course, you know, now you have to complement these 2 matrices from the left, or doesn't really make from the right, by 2 other matrices. And let me tell you now, I put here A and B beside each other, and the one which complement this is E. Now E comes from that I said, you know, that I said the 4 rows of H2 cross H2. if you find the canonical product of H2 by X2, it's going to really going to give me the rows of this matrix. Now, what really happens in here, you know, these rows are repeated in here. This row is repeated in here. That will compensate really for what we have here. If you really multiply this row to this row and this row to this row, you can see that you need 2b squared plus 2a squared, and you get it from here. So when you put E, A, and B together, the rows are going to be orthogonal to each other. And the news is that when you really consider the columns, when you really find the product, the dot product of the columns, you're not going to get for the horizontal one, you're going to get actually 2 times AB or minus 2 times AB, 2 times A squared or 2 times B squared. But for vertical ones, you're going to get really only plus or minus A squared plus B squared. So already we have one horizontal frame, namely EAB. And the second one is then can be easily constructed from the first one. Now, again, you can see that, again, people who are familiar with this sort of construction, they know that if you move around A and B, because of the property of being block-Gaulet, you really have to really only worry about really some columns. And there actually this E and minus E really will do the job of giving you what you're really looking for. So then you have to now complement the top part, and the top part you need again, from what we have, we can actually take up the top part. Indeed, actually, the top part was not easy, and the first example that I had, Tom proved that it's not correct. So the change had to be made, and of course, we learned a lot from the change that we made. And indeed, that putting all of these together, you're going to get this balancedly splittable OD1688. Now you can see that you get four frames. This is one of them, and the horizontal, the vertical, second one, and then you get this one, and you get this one. And indeed, actually, the vertical ones are going to give you, when you multiply each rows, you can see that here, for example, you're going to get minus A squared minus B squared. If you find the dot product of the first row and second row, you're going to get minus A squared minus B squared. The same, of course, for this one. You're going to get either A squared plus B squared minus A squared minus B squared. Now, the good news is that actually the construction works, even if you have complex OD. Now, what is a complex OD? You're allowing your variables to have coefficients. In the real one, the coefficients are either 1 or -1, because you're allowing A plus minus B. But for complex one, you allow the coefficients to be +-1 plus minus I, the complex I. Now, it just so happens that in this case, and for the complex ODs, you can actually assume even the variables to be complex valued. It just only works for complex ODs. And indeed, again, you're going to get frames, and the inner product every 2 rows, let's say blue one, you're going to get either A squared plus B squared or minus A squared minus B squared. However, of course, this is good because you can see that this fills the gap for cases that the real one doesn't work. Now we can even do better. You see that I like this one, this COD 211 so much that I had 2 copies of it actually, and one is black and the other one was in color. And again, the good news is that even if you really allow the coefficients, the variable, to be quaternions, quaternion units, I, J, and K, plus minus 1. Then the construction still works, and you're going to get a quaternitic orthogonal design, which is actually balancedly splitted. Again, you know, if you really pick up, let's say, the blue one or gray one, you really multiply the rows, and you're going to get, again, equiangular. They're going to be equiangular. And indeed, you know, this helps for the cases where odd multiple of 4n squared is not working. And we were quite happy when we noticed that not the construction working only for reals, works for complex and works for quaternions. I will not be surprised if it really works. I think, you know, the only important things that are really is used in here, the fact is the general property of orthogonality. You're really keeping the general property of orthogonality, and we get really this construction really works. Okay, thanks actually to the idea of Goulet. Okay. Okay, now there is so now we can now really say that there is a balancedly splittable Hadamard matrix with parameters 16n squared, 2n, 4n minus 1, and 2n. And of course, you know, you all know, I mean, people who really are familiar with designs, you know, these are really symmetric designs, and parameters of a symmetric design always coming from regular Hadamard matrices. But in here, of course, this shows really the number of vectors. I'm sorry, the dimension. This shows the dimension, and of course, this is the number of vectors, right? But n, of course, has to be an order of Hadamard matrix. So, for example, you know, you can take n to be 12, and you're going to get order 576. So, Hadamard matrix of 576, if it is constructed the way that I have shown you, it's actually balancedly splittable. And this leaves the existence of balancedly splittable Hadamard matrices for order 16n squared n odd. Keep in mind, you know, that here we have 16n squared, and n is odd. Let's say, for example, n equal to 3, so 144. We don't really know if there is a balancedly splittable Hadamard matrix order 144, which of course I'm going to pose it as an open question 3, right? Here we go. There is no, I don't know really the answer. To be honest, I really have no strong feeling against either there is no or there is one balancedly splittable Hadamard matrix of order 144. Indeed, you know, we don't know a single one of order 116 n squared n odd. And of course, the first order is 144. We don't know the answer. So this is a nice open question. And indeed, you know, even of course, you know, you noticed this morning, there's a lot of work on equiangular lines. So there are lots of people working, not only in combinatorics, even in applied harmonic analysis, you know. So, I mean, you expect to have a lot of really input. And there are actually a lot of results, actually, even on Hadamard matrices, you know, Hadamard frames and so on, right? However, of course, my interest is really picking up a special kind of Hadamard matrices, right? Now, there is a balancedly splittable quaternary Hadamard matrix with the parameter 16n squared. Look, this is exactly opposite of this one. This one, we don't know the answer here, 16n squared. There is one actually. And the assumption is, of course, n has to be the order of a complex. I'm sorry, not really a complex. Even better, quaternary Hadamard matrix. A quaternary Hadamard matrix, of course, is a Hadamard matrix you allow plus minus 1 and plus minus I as the entry. Rows, again, general orthogonality process. The rows are orthogonal. So there is one of these. So obviously then order 144 is there's one complex one of balancely splittable of order 144. The real one we don't know. Okay. Here we I'm defining something that already been defined this morning, namely equiangular lines in real or complex or quaternitic. And indeed, this morning also you notice that this relative bond, which is related to Delsarte-Goethals-Seidel, it's an old result, and it goes back to 1975. And Welsh band was almost found at the same time almost. But this has been named after Goethals, Delsarte, and Seidel. This is a relative bond. It really depends on the angle. So so every time you really achieve this bound, you're happy. And indeed, that now we can say that that there is always a twin flat equiangular time frame in R2n2 times 4n minus 1, with alpha, the angle being 1 over 4n minus 1, meeting the upper bound 1 up there. And of course, the assumption is the existence of a Hadamard matrix. If there is an Hadamard matrix, you can always find. Now, I said here twin, it's actually quadruple, actually. I should really say quadruples. However, you will see that for orthogonal designs, only the vertical ones are going to give you what we call a twin. That's why really I put in here a twin ones, okay. Okay, so for Hadamard matrices, there is a balancely splittable Hadamard matrix order 4n square and an order of Hadamard matrix. Well, okay, so there is a twin set of, this is sort of summarizing really what I have done so far, right? There is a twin set of flat ET meeting the ETFT. So that's what Goethals-Seidel bound. And no Hadamard matrix of order 4n square n odd is balancely splittable. So order 36 is not balancely splittable. And actually, there is a balancely splittable quaternary Hadamard matrix of order 16n square if there is a Hadamard matrix, if there is a quaternary Hadamard matrix of order 2n. And now the important one is the case of n equal to 6 for real ones open for n equal to 6. For the quaternary one is known, right? Now, there is a balancely splittable complex Hadamard matrix of order 4n square n odd, for which there is a complex, not really quaternary, complex. When you complex Hadamard matrix, you allow the entries to be any complex unit complex number. However, this special case, a special case here which works, it's called Butson Hadamard matrices. Namely, the entries are the nth root or the roots of unity. So the construction that I just showed you works even for Butson Hadamard matrices. Namely, there is a Butson, a balancely splittable Butson Hadamard matrix of order 4n square, of course, if there is a Butson of order n. Now, this is quite interesting because of the fact that it resolved the order 36. So for order 36, we have a flat now complex equiangular line set, consisting of 16 vectors in C6. Something that that definitely is missing, and indeed, you know, I sort of didn't go through the other part, namely, I'm pretty sure, you know, because of the I showed you that every time you have a balanceless splittable Hadamard metric, you always find pair of unbiased Hadamard matrices. So the question is, what for orthogonal design? Yes, for orthogonal design, you get unbiased orthogonal designs. Now, what is an unbiased orthogonal design? Off diagonals. Again, you know that when you multiply, you get off diagonals always, you know, plus minus. Weighted sum of square of variables, depending on really what sort of OD you use. You know, for example, there is an OD of order 12 in 4 variables. One is repeated 1 time, other one is repeated 2 times, another one is repeated 3 times, another was repeated 6 times. So when you go really to order 576, you're going to get every of these variables. One of them is 48 times repeated. The other one is 96 times repeated. The other one is 144. And the last one is 288 4 times repeated. However, you know, when you multiply them, you're going to get off diagonal is a weighted combination of a squared, b squared, plus b squared, plus c squared, plus d squared. I give this example to show you how versatile the case is. Indeed, really, you have a lot of choices on A, B, C, and D. So it really gives you a lot more for Hadamard matrices than for really what we know really. The case also works, you know, for quaternion orthogonal design. It works for quaternionic orthogonal design. It works for all of these. And indeed, of course, you know, the options of really playing around with variables, putting different values for variables. And indeed, actually, you can put for variables, you can put matrices. Instead of variables, you can put matrices. But you have to be careful, because in here, we only assume that the variables are commuting. All the things are really on the assumption that the variables are commuting. But when you put matrices, you have to make sure that you have an evolution there. Namely, when you take the transpose of the matrices, multiply a matrix by the transpose of the other matrix, it is symmetric. So you have to assume something like that, which of course there are plenty of those. And indeed, really, there is some asymptotic results that one can get. Indeed, you can go to the biangular frames, and you get biangular frames and so on. And I am right at the end of my 50 minutes. So I just stop here. Thank you.
Thank you.
Any question?
What he said.
How do you know that
Yeah.
I'm very?
Yeah, I know. I was expecting.
Thank you for the nice talk. You know that I'm very interested in the mutually unbiased Hadamards, right? So these give real MUBs, and by the way, for other people listening, those are exactly the same thing as 4-class Q polynomial association schemes with both the Q bipartite and Q antipodal property.
Your work, I know. Yeah.
It doesn't matter whose work it is,
of course, of course, I'm very interesting one, right? Yeah.
The standard basis is one fiber, and each Hadamard is another fiber. Do we have any way to increase the number of pairwise unbiased Hadamards as the size grows? We have the Cameron-Seidel examples, but do we have any examples with you know?
Very nice question. Of course, you know, I have thought of it. You know, I have some ideas, you know, but still I need really to work on it, right? Yeah. Of course, you know, the first question you could have asked is if you have two frames, you know, if you use the two frames, right, and their complements, are they going to be really different unbiased different ones, and the matrices you get from there, are they really unbiased? I think, you know, I have to ask Tom, you know, my graduate students really to do that. I'm sure he's now listening, and to do that, and of course, you know, there are plenty of different ODs. You know, if we use different ones, do we really get different unbiased ones, right? And different really to increase, as you said, the number of unbiased ones, right? Yeah, that will be really interesting if it is possible at all, right?
Thank you. I don't think anyone's maintaining a table of how many we can get.
No, unfortunately, no.
Thank you.
Other questions?
Yeah, thanks for a nice talk. I have what's maybe a naive question. So the sizes of the ETFs that you're getting can also be obtained from Hadamard matrices in a different way. And
I know that. Yeah, okay.
If you looked at this, so like maybe you could show us very early on you had a 6x16, and then you had the Gram matrix of that. I don't know if you can find this in your slide, just to
of course. Yeah.
For me to explain what I'm talking about. Oh, sorry.
Do you want to look at the ODs?
So far back.
Yeah, okay. The ODs are also the same as those, right?
Well, this is what I wanted to ask.
Yeah.
So we better make sure we're talking about the same thing.
Yeah, here you go.
Let's see. So here, I'm not quite sure if this is it. So you had a 6x16. Is this the Gram matrix of it? Like this is
no. This is the actual matrix.
This is okay.
This is Hadamard matrix.
So suppose you take the bottom part, that bottom 6x16.
Yeah.
Yes, exactly.
Yeah.
And then you make its Gram matrix.
Yeah.
So its Gram matrix, I think in this case, is going to have 3s going down the diagonal, and then the off diagonal is going to be a bunch of plus or minus 1s.
Yeah, I mean, if you take units, right? Yeah, I showed that one, right? Yeah, here we go.
I hear. Okay, very good. Okay, so if you replace all of those 6s with 2s, let's say, and then do a half of that, that's a Hadamard matrix. And this will always occur, this phenomenon will always occur for the sizes of real ETFs that you're getting. And I wonder if there's a relation between these two Hadamard matrices.
I don't know, but if, well, I don't know. But of course, you know, if you take the other part, and as I said, you know, once you subtract the two, you're going to get Hadamard matrix, which is actually unbiased with the original one, right? So you take the complement of the F1, right? And find the gram of that and subtract. Then, and of course, you have to balance, you know, the entries. Then you get a matrix which is actually unbiased with the original one.
Mm-hmm.
Yeah, that's what you get, right?
Okay. Yeah, I don't know what kind of answer would be satisfactory for me, but just I know that there is another Hadamard, just something I know. There's another Hadamard matrix that's sort of the same size that you're playing with that's around in the ether, and I just it may be something to see if it wants to play this game too. But thanks again for a nice talk.
Thank you for your nice talk. I really enjoyed it. Well, it seems like it's going to be a shorter day today.
I have a comment rather than a question.
Yes.
That in the construction, you're working with unimodular entries, and then you get unbiased unimodular matrices.
Right.
And so I think over the course of your doing this, you came up with some examples of unbiased Butts and Hadamard matrices that
Absolutely.
I don't think had been seen before, right?
Yes. Yeah, well, we just actually working with the simplest possible Butson, namely 1, 1, 1, and 1, let's say theta square, and 1 theta square theta, with a 3 by 3, and from there we got 36. And then from 36, we got actually unbiased, yes, unbiased Butson, right? And of course, as I said, even with quaternionic ones, you can get unbiased one, right? Yeah. For the general structure, really only depends on the general property of orthogonality. Yeah. And that really works, So I wouldn't be surprised if, let's say, for example, for type 2 also, I mean, for type 2, you can do a lot, right?